Welcome back to the deep dive. Um, if you're tuning in today, I'm guessing you've spent your fair share of time staring at a live camera feed, just watching a laser dance around in a droplet of resin.
Yeah, it's a very specific kind of hypnosis, isn't it?
It really is. We know you are living in the world of submicron resolution. You know your way around a nanoscribe. You understand the difference between a voxel and a pixel. And you probably have some pretty strong opinions about slicing distances.
Oh, absolutely. But usually when we talk about two-photon lithography or 2pp, we're obsessing over things like photonics, wire bonds, or micro-optics. Metamaterials, we talk about structural integrity and refractive indices.
Right, the hard stuff. But today we are taking a major pivot. We're taking that high precision hardware and pointing it at the wet, messy, completely chaotic world of biology.
Which is, frankly, it's about time. For years, the quote-unquote killer app for 2pp in biology has been theoretically possible, but practically just very elusive.
Yeah, we've been able to print these incredible structures, tiny Eiffel towers and microscopic lattices, but getting actual living cells to care about those structures is a totally different story.
Exactly. And that brings us to the premise of today's deep dive. We're looking at a paper by Mimetz et al.,
Mm.
published in Cell Stem Cell in 2026, which essentially asks if we can use 2pp to solve the single biggest bottleneck in tissue engineering right now.
And that bottleneck is the organoid problem. I think anyone remotely adjacent to bioengineering has heard the term growing mini organs in a dish.
Well, mini organs is kind of the PR term. Unstructured blobs is often closer to the reality.
Right, just a ball of cells.
Yeah, don't get me wrong, organoid technology is a massive breakthrough. You take stem cells, you put them in a gel, and they self-organize. But they usually get stuck in what biologists call a fetal state.
They're immature.
Very. They're like a construction site where all the workers showed up but somebody lost the blueprints. They just don't have the architecture to function like an adult organ.
So you have this blob that technically could be an intestine, but it doesn't digest anything. It doesn't have the right cell types to fight off bacteria. It's essentially a biological prototype that never actually goes into production.
Precisely. And the core hypothesis in this 2026 paper is that the missing ingredient isn't chemical.
Yeah.
It's not some magic growth factor that we just haven't
Yeah.
discovered yet. The missing ingredient is geometry.
The physical architecture of the environment.
Yes. Which brings us right back to the hardware.
Yeah.
To test this, you need to create a very specific geometry with micron-level precision.
Mm.
And you just can't do this with standard soft lithography or molding.
You need the freedom of 3D writing. So for the 2PP experts listening, let's look at the actual setup they used. They were running nanoscribe GT2 systems, and they were writing into IPS resin on ITO-coated slides using the dip-in laser lithography configuration. But stop there for a second, because IPS is an acrylic resin.
Right, it's hard.
Yeah, it's great for smooth surfaces, but it is rigid. It's not exactly bio-friendly when you're trying to mimic the softness of a human gut. Why didn't they just use a hydrogel resin? We have printable bioinks now.
That's a really crucial distinction, actually. They didn't print the scaffold directly. They used the 2pp process to print the master mold. They created the negative, and then they cast a collagen and matrigel mix into that mold.
Ah, okay, so they decoupled the geometry from the material stiffness.
Exactly. If they had printed the final scaffold out of IPS, the geometry would have been flawless, but the cells would have hated it because it's essentially plastic. By printing the mold, they get that submicron nanoscribe resolution, but the final environment for the cells is a soft biological hydrogel.
That makes total sense, but man, anyone who has tried to demold high aspect ratio pillars knows that is an absolute nightmare.
Oh, it's the dark art of soft lithography.
You're peeling a soft gel off a rigid forest of tiny spikes. It just wants to tear.
It does. And looking at their parameters, they had to be incredibly careful to pull that off. They used a slicing distance of 1 micrometer and a hatching distance of 600 nanometers.
600 nanometers hatching, that is tight.
It had to be. They needed that surface to be practically glass smooth. Because if you have significant stair-stepping or scalloping on the sidewalls from a larger hatching distance...
The gel mechanically locks into the mold.
Exactly. When you try to peel it, you just rip your pillars right off. Plus, we know that cells can actively sense surface roughness. If the mold has ridges, the gel has ridges, and that creates noise in the biological signal.
Right, so they're printing these super smooth molds. What exactly are they trying to replicate? What's the golden geometry here?
They are mimicking the crypts of Lieberkühn.
Which sounds exactly like a location in a high fantasy novel.
I know, it really does. But it's actually the architecture of your small intestine. Your gut lining isn't just a flat tube. It's covered in villi that stick up and crypts that dig down into the tissue.
They're microscopic pits.
Invaginations where the stem cells live. In a mouse, these are roughly U-shaped tubes. And this is where the deep dive really gets going. Because they didn't just print one theoretical crypt, they treated this like an engineering parameter sweep.
They went full design of experiments on the biology.
They absolutely did. They printed pillars to create wells ranging from 30 micrometers in diameter all the way up to 180 micrometers. They effectively built an array and asked the cells, okay, what size do you actually like?
And I love this part of the paper because it really shows the brutality of physics. You might look at biology and think, oh, it's adaptable, the cells will just figure it out.
Yeah.
But that is not what happened.
Not at all. They found a very hard cutoff. The magic number was exactly 50 micrometers. When the wells were 50 microns wide, the cells organized into a beautiful single layer, lined the walls perfectly, and looked functionally identical to a real crypt.
But what about the bigger wells, like the 200-micron ones? That is still tiny. To the naked eye, it's invisible. Why did the biology completely fail there?
The authors describe it as a loss of patterning. In the 200-micron wells, the cells essentially didn't know which way was up.
They got confused.
Yeah, they started growing inward, filling up the tube entirely, or they'd invade outward into the matrix. It was just chaotic. Without that very tight spatial constraint, the self-organization just fell apart.
So the geometry isn't just acting as a container, it's an active instruction. It's telling the cells, line up here, stop growing there.
Exactly. And the most elegant part is that a 50-micron diameter matches the exact in vivo size of a developing crypt in a mouse embryo. So the nanoscribe essentially allowed them to reverse engineer the physical boundary conditions of a living embryo.
Right, so we have the what? 50 microns is the absolute winner. Now we need the why. We've established that the cells in the 50-micron pits, quote-unquote, grew up. They transitioned from that fetal state to an adult state.
Yes. Within just 6 days, they differentiated. They became adult cell types. Pannid cells, which provide antimicrobial defense, and enterocytes, which actually absorb nutrients.
But you got jobs.
They got jobs.
But how does that actually work? Because the scaffold itself is chemically inert. It's just collagen sitting in a specific shape. How does a shape reach into the nucleus of a cell and flip a genetic switch?
This brings us to mechanotransduction.
A favorite buzzword. Let's unpack that for everyone.
It literally means converting mechanical forces into biochemical signals. And in this specific case, the mechanism is surprisingly direct. It's all about crowding.
Crowding, like being stuck in a crowded subway car.
Very similar, actually. Think about the geometry of that crypt. A 50-micron well is tight. When you pack cells into that curve, they have to physically squeeze against each other. And this squeezing applies tension to the cytoskeleton.
The internal scaffolding of the cell.
Right. And that tension on the cytoskeleton physically connects to the nucleus. It literally pulls or compresses the nuclear pores. And this physical deformation controls the traffic of a very specific protein called YAP1.
Okay, YAP1, this is the star of the show in this paper. What is its role?
YAP1 is basically a master growth switch. When a cell has plenty of space, like if it's sitting on a flat plastic dish or in one of those big 200-micron wells, YAP1 flows freely into the nucleus.
And when it gets into the nucleus, what is it doing?
It's essentially shouting, divide, expand, stay young. It keeps the cell locked in a highly proliferative fetal state.
So high nuclear YAP1 equals eternal youth.
Correct. But when you force those exact same cells into the 50-micron crypt, the crowding happens. The mechanical stress physically blocks YAP1 from entering the nucleus.
It gets stuck out in the cytoplasm.
It gets locked out of the control room entirely. And without YAP1 in the nucleus screaming at them to grow, the cell defaults to its next biological program, which is to mature. It turns on the differentiation genes.
That is wild. So the nanoscribe didn't just print a cup for the cells to sit in. It printed a mechanical vise that squeezed the youth protein right out of the nucleus.
It directly connects your fabrication tolerance to a genetic outcome. Think about that. If you print that well, 20 microns too wide, the squeezing stops. YAP1 goes back into the nucleus, and the tissue stays fetal. The physical tolerance of your printer dictates the biological age of the tissue.
Now, I have to play devil's advocate here for a second, because correlation is not causation. Maybe the cells just really liked the curvature. How do they definitively know it was the crowding and the YAP1 levels driving this?
This is where the biology in the paper gets really rigorous. They ran a dilution experiment. They took the perfect 50-micron scaffolds, the ones that worked beautifully, but they seeded them with significantly fewer cells.
So it's the exact same geometry, but lower density, less crowding.
Right. And the maturation failed. Even though the shape was perfect because the density was too low, the cells weren't squeezing each other, YAP1 stayed right in the nucleus and they remained fetal.
Okay, that pretty much nails it. It's not the curve itself, it's the density that the curve enforces.
But they actually went one step further to prove the genetic side of the equation. They engineered mice with this specific mutation called TIAP1.
What does that do?
It allowed them to use a drug, foxycycline, to force a mutant form of YAP1 to stay active and in the nucleus, no matter what mechanical forces were applied.
So they basically rigged the game. Even if the cells are squeezed, the growth switch is super glued to the on position.
Exactly. They put these genetically altered cells into the perfect 50-micron scaffolds. They were crowded, the shape was right, but because the researchers chemically forced YAP1 to stay active, the cells outright refused to mature.
They completely ignored the geometry.
Yes, because the genetic signal overrode the mechanical one.
That is a definitive smoking gun. It maps the entire pathway flawlessly. Geometry leads to crowding, crowding leads to low YAP1, low YAP1 leads to maturation.
It's a beautiful loop of logic. And for our listeners, it really validates why we obsess over submicron resolution. We aren't just chasing numbers on a spec sheet. In this context, the difference between 50 microns and 100 microns is literally the difference between a functional organ and a tumorous blob.
Okay, so we have a remarkably cool way to grow mouse intestines. But as interesting as developmental biology is, our listeners are usually looking for the application. The so what? Why does this matter for medicine?
So what here is huge. This model creates a functional platform for understanding disease, specifically inflammation and inflammatory bowel disease, or IBD.
This was the part of the paper involving PGE2, right?
Yes, prostaglandin E2. It's a key inflammatory molecule that spikes when you have tissue injury. And evolutionarily, it is very useful. If you get a physical cut in your gut, PGE2 tells the local cells, emergency, stop digesting food, revert to a fetal state so you can divide quickly and patch the hole.
So in an acute injury, going back to a high YAP1 fetal state is actually a critical survival mechanism.
Exactly, it's just wound healing. But in chronic diseases like IBD or Crohn's disease, the cells get stuck there. They're constantly bathed in this inflammatory signal, so they stay locked in that fetal repair mode state.
They never go back to work. They're trapped in this loop of trying to fix a wall that's already patched, but they refuse to put the tools down.
Right. So the researchers asked a fascinating question. Can our engineered geometry fix this? They took healthy adult organoids and hit them with PGE2. And the cells did exactly what we expected. They reverted to a fetal state. They started heavily expressing SCA1, which is a known marker for tissue damage.
So now you have functionally sick cells.
And then they took these sick, confused cells and dropped them into the 50-micron 2pp scaffolds.
And what happened?
The geometry overrode the chemistry.
Wait, really? The physical shape was stronger than the inflammatory drug signal?
Yes. The physical crowding inside those 50-micron crypts forced YAP1 out of the nucleus, effectively ignoring the PGE2 signal entirely. The cells resolved the inflammation on their own and returned to a healthy homeostatic state.
That is profound. I mean, we usually think of treating inflammation exclusively with drugs, anti-inflammatories, steroids, biologics, but this strongly suggests that the actual microstructure of the tissue itself acts as a medicine.
It acts as a physical template for health, and this has massive immediate implications for drug screening.
Break that down a bit. How does this change how big pharma tests drugs?
Well, imagine you are a pharmaceutical company testing a new biologic for IBD. You're probably testing it on cells grown in a flat petri dish or a generic blob organoid. Those cells are highly likely to be stressed or in the wrong geometric state simply because of where they are growing.
So you might get a false positive or worse, a false negative, because the baseline biology of your test subject is artificially flawed.
Exactly. If the cells in a flat plastic dish have high nuclear YAP1 just because they aren't crowded enough, they might look inflamed even when they aren't.
Yeah.
By using these 2pp printed scaffolds, you provide a standardized, physiologically correct baseline.
You know that if the cells are acting weird, it's definitely the drug, not because they hate the plastic dish they're sitting in.
Right. It effectively turns 2pp into a standardizing tool for the entire pharmaceutical industry. You print the control environment. And that is a highly scalable commercial application. We aren't just talking about printing one-off scientific experiments for a paper anymore.
We're talking about printing massive arrays of thousands of these precise crypts to screen drugs with an accuracy we've never had before.
Which brings us right back to the machine. The nanoscribe, or whatever high-res system you're running, isn't just a tool for making lenses or metamaterials anymore. It's a tool for enforcing biological order.
It creates the boundary conditions for life. It completely validates the idea that you cannot separate the biology from the physical mechanics of the environment.
I completely agree.
I want to zoom out a bit as we wrap up today. We started this deep dive with the frustration that 2PP didn't really have a killer app in bio. I think we have found a very strong contender here.
It definitely moves the field from just bioprinting cells to bioprinting instructions. We aren't trying to micromanage and place every single cell in the exact right spot that is way too slow and prone to error. We are printing the landscape and letting the cells self-assemble based on the physical rules of that landscape.
Form dictates function is the old engineering adage, but here it is entirely literal. The form is the function.
And for you listening, it really highlights why those painful hours optimizing print parameters actually matter. That 600 nanometer hatching distance, the specific resin choice, the aspect ratio of the mold, those aren't just arbitrary fabrication specs to keep the printer happy. They are direct biological inputs.
So here is a final thought to leave you with. We now know that a 50-micron pit acts as a mechanical instruction that tells a stem cell to become an adult intestine. That is one specific biological program unlocked by one very specific shape.
Right.
But the human body is full of incredibly complex microgeometries. You have the nephrons in the kidney, the lobules in the liver, the trabeculae in the heart.
All defined by complex 3D architectures.
So what happens if we map those? Could we use two-photon lithography to 3D print the instruction set for an entire liver? Not by printing liver cells, but by printing the precise geometric niche that physically tells a blank stem cell, hey, you are a liver now.
It strongly suggests that the code for organ regeneration might not be entirely written in the DNA. A massive part of it is written in the geometry. And we are finally building the machines capable of writing that code.
We have the hardware, now we just need to figure out the shapes.
That is the new frontier.
Thanks for diving in with us today. Keep your hatching distances tight and your lasers focused.
See you on the next deep dive.